Okay, next question, 39 of the 6th edition. This should correspond to question 44 of the 7th edition. Okay, so 39. Okay, it tells us, or it asks us, how strong is the electric field between the plates of a 0.80 microfarad air gap capacitor if they are 2 millimeters apart and each has a charge of 72 microcoulombs? Oh, what the hell? Let's draw this. So I've got my two plates, and what's given? I'm given that the capacitance is equal to 0.80 times 10 to the minus 6 farads. Okay, that's the capacitance. I'm told they're 2 millimeters apart. Exact 2.0 millimeters apart. Okay, and each has a charge of 72. Each has a charge of 72 microcoulombs. Okay, well, okay, that would mean that here we've got Q and there we've got minus Q, where Q is equal to 72 times 10 to the minus 6 coulombs. Right, okay. Now I'm asked for the strength of the electric field. Now remember, this will simply be the electric field strength. Remember, for capacitors, we just write it's a potential difference between the plates, V over D, D the distance between them. Okay, so I am after E, how strong is the electric field. So this is what's asked. I can use this because it's two parallel plates, so that means we can assume that the electric field's uniform in between, which means we can use this formula. We use the distance, perpendicular distance between the two plates. Okay, so what don't I have? Well, I don't have the voltage, but it's a capacitor. I've got an equation for voltage, and that is the following. Q equal to CV, or in other words, V equal to Q over C. Okay, do I have Q? Yeah, that's given. Do I have C? Yeah, that's given. Well, okay, then I've got V. So E is equal to Q over CD. Right, and now I just substitute the values. So this is 72 times 10 to the minus 6 coulombs over the capacitance, 0.80 times 10 to the minus 6 farad, times the distance, 0.0, okay, 02. Now, perhaps I should just have written 2.0 times 10 to the minus 3. Well, okay, fine. This is okay. And now I just calculate this. So this is going to be 72. 10 to the minus 6 is cancelled. Is that really the case? Yeah, it is. 72 divided by 0.8 equal divided by 0.002, which is, yeah. And I'm going to provide two significant figures, so 4.5 times 10 to the 4, and this is electric field, voltage over meters, so volt over meter, volts per meter. Okay, well, that's 39. Okay, next one is question 42. That brings in some dielectrics, where you now place something in between the two plates, which has the effect of increasing the capacitance by weakening the electric field in between. Right. Okay, so let's read the question. It says, it just asks for what is the capacitance of two square parallel plates. I give the dimensions, 5.5 centimeters on each side, two square parallel plates, okay, and that are separated by 1.8 millimeters of paraffin. Okay, so this is simple. So we've got the formula for the capacitance of two parallel plates. We've got that, so you can work that out. And if you've got a dielectric in between, then you just multiply your old capacitance value with a dielectric constant of the material, of paraffin in this case. Okay, so now that we can look up, it is in the textbook. It's a table of values. The capacitance is going to be equal to, if it were just the two parallel plates separated by air, well, technically by a vacuum, but there we have it. I don't know if you'll be able to see it. Let's see. Okay, so here's a bunch of values. Actually, for vacuum it is 1, for air it's not really 1. 1 atmosphere is a little bit more. So what we're after? How am I reading right over it? Ah, there it is at the top. Perfect. 2.2. Okay, 2.2. And so this is if it was just with air, or strictly speaking just with vacuum. But we've got paraffin in between, so you have to put in the dielectric constant for it. Okay, and this is 2.2, and this permittivity constant, this was 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. Yeah, that's right. Times the area. Okay, so what's the area of the plate? Okay, it's 5.5 centimeters on a side, so that's squared, that's the area, and it's separated by how much did it say? It was separated by 1.8 millimeters. Okay, so this is going to be 0.0018. Oh, I should put meters there. Meters. Okay, and now we just have to calculate this expression. So 2.2 times 8.85 times 0.055 squared divided by 0.018. No, 0.018. That right? Yeah, that's fine. Times 10 to the power minus 12. Good. And I'm going to provide the answer to, let's see, my data is given dimensions to least number of significant figures used here, 2, so I'm going to provide also to 2. So it is 3.3 times 10 to the minus 11. And what is this capacitance? So it is farad. Good, easy. Right, now 47. That's the last download problem. It should be 53 in the 7th edition. This is just now calculating the energy stored. I used to put the charge on the plates of a capacitor. Let's see what it says. A cardiac defibrillator is used to shock a heart that is beating erratically. Okay. A capacitor in this device is charged to 5.0 kilovolts and stores 1200 joules of energy. What is its capacitance? Okay, now relating and getting to the energy stored in capacitor, we had formulas for that. Remember, 2 in fact, so we'll just use one. We'll use that one. That one will be simplest to use because we've got the voltage that's given, and we're given the potential energy. So we're just after C, the capacitance. Okay, so we just straight up write down the formula. B is equal to half CV squared. I'm after C, so C is equal to 2 times potential energy over V squared. Okay, now we just simply substitute the values. 2 times, and this was given, 1200 joules over voltage squared, 5000 volts squared. And let's calculate that. So that's 2400 divided by 5000 squared. Yeah, like that. Okay, so that gives us how many significant figures I'm going to use. Well, it's not really clear if I should use 2 or 3. I think 2 is okay. So it's not clear if these are 2 or 3 or 4 significant figures. I would say at least 2, perhaps possibly 3. Okay, 9.6 times 10 to the minus 5, and this is capacitance, so it is farad. Okay, and that's it.